All right, good afternoon, everyone, or good morning whenever this finds you. Today we are going to be looking at the practice problems from the review section of our Unit 3 packet. This is on pages 21 through 24. Now, if you have not had a chance to try these problems yet, make sure you stop and do these problems before you watch this video where we're going to go through and add some explanations. The idea is if you are just watching me talk about this, you're probably going to retain none of this information and you won't really gain any benefit out of the review. But if you have tried every problem, then you'll have some ideas about what you're thinking right now. And when you come through and watch me talk about the review, you will either be confirmed in what you think and retain that information better, or you'll find out you were wrong. And that also is going to help you retain the information better than if you just sit here and passively watch the video. So, let's get started. In problem number 1, we have a stunt car, and it's for a movie, right? It's driving off a cliff. We need to draw the free body diagram of the car while it moves through the air, and we can assume that all the cars have the same mass, everything, it's pretty straightforward. I'll be honest, I think we copied some of the wording out of another problem here. If I'm going to draw my free body diagram over here, I would go and I'd be like, all right, well, we've got this car. It's off a cliff, right? It drove off a cliff. And I'm just going to go through my series of questions that I ask myself when I make a free body diagram. Is there a push or a pull to the right? Well, the wheels are in the air now, so they can't push on the ground. So the car's not being pushed forward, so there's no arrow there. Is anything pushing it upwards? Well, we're ignoring air resistance, so as it's falling through the air, we wouldn't have any upwards arrow from air resistance because in this unit we're going to always ignore air resistance. Same deal with any arrow backwards is the brakes and the wheels are all in the air. Nothing can really stop it from moving forward, and we're not going to have any air resistance, so that's not going to fight its forward motion. That car is on Earth, though, which we can assume for all of our problems in this unit, and that means it's affected by the force of gravity. That leads us to the free body diagram for any projectile in this unit. It's going to look just like this because a projectile is only under the influence of gravity. Now, if we want to look at the horizontal component of this object's motion, one thing that we might notice is that in the horizontal direction, the side-to-side direction, we have balanced forces. That means we are traveling at a constant velocity, right? No forces is a balanced force, and that means we're at a constant velocity. We're going to call the forward direction positive, and so for our xt graph here, I'm going to put all my labels on here because I like it to be nice and tidy. For the xt graph, I will have a constant slope. That slope will never change because I'm in constant motion. And on an xt graph, the slope is your velocity. If your slope never changes, your velocity never changes. Now when we move over here to the VT graph, I'm going to label that yet again. We are going to now look at a VT graph, and the VT graph is our position on graph, right? The data points are our velocity. The big difference here is that our line, wherever it is at any given point in time, is going to represent how fast we're going. What that means for us is that our line should be flat on a VT graph because that means at every point in time you're going that same speed. Now, if we want to talk about the vertical components of the object's motion, we're again going to look at an xt and a VT graph. I'm going to put my labels on, which you might not necessarily have to do if we don't give you data, but we do expect you to label it xt, and actually we do want everything, right? I want your labels on there for everything. I want to know that you know that meters per second is what we'll be measuring velocity in here in physics. And again, on our xt graph, the slope is our velocity. And the data points that form our line are our velocity on the VT graph. Now, if I look in the vertical direction, I will notice that I have unbalanced forces. That means I have changing velocity. In this case, my unbalanced force is in the downwards direction, the negative direction, which means I am speeding up in the negative direction. What that means for me is on my xt graph over here, I will start out with no slope because my velocity is very low at the very start as I begin to fall, and it's going to become increasingly negative in its slope, right? The slope is our velocity. If we don't have slope at the start, we don't have velocity. And as we get a steeper slope, we have more and more velocity. In this case, that slope is becoming more and more negative, so it's more and more negative velocity, meaning we're speeding up in the negative direction, which lines up with what our FBD tells us and what conceptually we know an object does when it falls, which is speed up as it goes downwards. Up here, right as that car drives off the cliff, it's not moving up or down at all as it leaves the cliff, but after it's in the air, it's going to fall, and our velocity is going to get more and more and more negative. These are going to be what the xt and vt graphs look like for the horizontal and vertical components of any horizontal projectile's motion. The slope might be a little bit different in some cases, but overall, these are your shapes you're going to be looking at. Now, number 1 was a long one. Let's move on to number 2 here. In number 2, we've noticed that in lab, we tried launching things out of that cannon, and we saw that the horizontal speed the car was launched at had no relationship to how long it was in the air. It might affect where it lands, as in how far away it lands. However, no matter what speed it's traveling at, there's going to be no connection between that speed and the amount of time that it is in the air for. Therefore, we'll notice that each one of these is a 30-meter tall cliff. If we want to rank them based on the amount of time the cars are in the air, well, they're all going off the same cliff. That means they're all going to be in the air for the same amount of time. That's because no matter what, they'll all be influenced by the force of gravity, and they will all accelerate downwards at that same negative 9.8 meters per second squared. That's true for all of them, therefore, they'll all accelerate downwards at that rate. Now, as we continue through these practice problems, we're going to ask you a few more of that same style of question about each variable that you could change for the car. So, from our observations in lab, we noticed that the horizontal speed that a car is launched with has a direct relationship with how far away it will land. So if we're looking at these, we'll note they are all going off the same cliff, right? Each one is 30 meters tall. What that means is they will all have the same amount of time in the air. Now, our horizontal motion is constant velocity. That is, x equals vt. Therefore, since they all have the same t, the only thing that can affect x is going to be our speed. In this case, object A has the greatest speed, and so it is going to land the furthest away. Object C has the next highest speed, object B, and then lastly object D. Again, the key thing we'd be looking for in terms of understanding here is that the speed that it launches off the cliff with affects where it lands, but does not affect the amount of time it's in the air for. Now in this next one, we are going to compare our observations from lab again. In this one, we're looking at different heights in which the object is launched from. In lab, we learned that the height an object is launched from has a direct relationship with how long that object is in the air for. That means that object A down here, having the greatest height, will be in the air for the greatest amount of time, followed by object D, then by object C, and lastly by object B. We're just going in order of tallest to shortest. Lastly, in lab, we noticed that the height that a car is launched from has, in many cases, this is going to look like this, right? It is going to actually be a direct relationship with how far away it will land. That's because it's going to increase the amount of time that it's in the air for. More time to travel means more distance traveled. In this case, all of them are traveling at the same speed, and what that means is that the only thing that's going to affect the distance they land at is how long they have to travel. In this case, object A, having the greatest height, will have the greatest amount of time to travel and will land the furthest away. Object D then has the next greatest travel time and will land the next furthest out, followed by object C and by object B. These are the kind of questions we like to ask you because they help us understand if you know the relationships between the different variables and what's going to happen. Now, turning to page 23 here, we're going to need a calculator. I'm going to pause for a moment to let you grab that. Now that you have your calculator, or hopefully have it, we're going to continue on and do a few of the math problems, working them through together. I'll try to show as many of my steps as possible to help you solidify your math understandings. Remember, you can pause this video at any point or slow it down to follow along. A ball, number 6 on page 23. A ball rolls off a balcony at a speed of 2.6 meters per second. The table is 4 meters above the ground. What is the range of the ball? So if my ball is rolling off a balcony, I know we see off when we picture a vertical direction, but we need to picture that ball rolling along the balcony before it falls off. That tells us that since it's rolling along the balcony, that it's going to be 2.6 meters per second in the horizontal direction. The table is 4 meters above the ground. That tells us that that ball is going to fall 4 meters when it goes off the edge, so I'm going to make my 4 negative. I want to know what is the range of that ball. That is, how far away does it land from the table? So that's going to be a side-to-side direction. Our horizontal information will always be connected with the equation x equals vt, and our vertical equation will be always connected with the equation x equals 1/2 at squared plus v1t. I'll remind you that in this class we found that there is a shortcut of saying x equals negative 4.9 t squared whenever we're dealing with a horizontal projectile, because in those cases we know v1 is always 0 meters per second. I'll use this shortcut from here on out, but on the first one I'll show you it without the shortcut, just to make sure you have all the different ways to do this. Alright, we want to know the range of the ball. Now, our rule in any projectile problem is that when we have a horizontal projectile, we'll start by finding time. In order to find time, we need to look and determine where we have enough information. If I know both x and v, I have enough information to find t, starting on the horizontal side. However, I don't have x, so I can't start there. On the vertical side, if I know xv, the vertical height, I'm able to start on the vertical side when it comes to time to solve for time. I will plug my numbers in. Negative 4 is my vertical height. A is negative 9.8 meters per second squared, because we're here on Earth. I don't know my time, so I'll just leave it as t. I know v1 is 0, and again, I don't know time. Now, what this will do for me, anything times 0 goes away, and I can simplify 1/2 times negative 9.8 to be negative 4.9. Those are numbers that I just happen to remember, so I don't necessarily need my calculator to do them. However, as I continue to work these, let's see if I can find a spot where you can see my calculator too. That looks pretty good. As I continue to work these, we'll need to make sure we run calculations. Don't take shortcuts. One thing I know I've seen getting in people's way is that they might take a shortcut. They might not show every step. So my next step is to get the negative 4.9 away from t squared. I have to do that before I can actually calculate t, because I need t squared by itself to take the square root and get rid of the square. Negative 4 divided by negative 4.9 is going to give us 0.816 with a little rounding. Keep in mind that's not time yet. We will need to take the square root of our answer in order to find out that our time is 0.9 seconds. I can now plug that time in to the equation x equals vt. My velocity was 2.6. My time was 0.9. And I can find that my ball traveled 2.34 meters. How about that? If you put a box around your answers, that really helps us when we come and help you with your work. It helps us really instantly see where your answer is, and that helps us quickly check if you have it right or not. All right, let's take a look at our next problem. Again, this problem is a horizontal projectile, so it's going to be governed by x equals vt, the constant velocity equation for the horizontal side, and I'm going to use my shortcut on the vertical side, and x equals negative 4.9 t squared. Now, I'm spraying water out of a garden hose that's held horizontally above the ground with a vertical height of 1.5 meters. Now, since my water falls 1.5 meters, I'll make that a negative. Now, my water will spray a distance of 3 meters. That sounds like how far away from me it's going to land. So that tells me that I know the horizontal distance. However, I want to know how fast that water is going as it comes out of the hose. What's kind of interesting is this is actually a calculation you can do if you're ever curious, and you can actually determine how fast the water comes out of your hose at home simply by taking some measurements like this. Don't even need a stopwatch, just a ruler and the hose. So now what we're going to do is we are going to plug our numbers in. Our vertical height was negative 1.5 meters, and since we know our vertical height to start with, we will start on that side. I'll plug it into my simplified equation here, and I will start to simplify that so I can solve for t. In order to do that, I'll get negative 4.9 away from t squared, negative 1.5 over negative 4.9, and that's going to give us t squared is 0.3. Take the square root, and that's going to give us the time of 0.55 seconds. I can bring that time over here, and I can say my 3 meter distance is equal to my velocity times 0.55. Take 3, divide it by 0.55 to get v by itself. And I'll find my velocity to be 5.45 meters per second. Again, just going to put a box around it to help us notice it. Now, our next problem is another one of these. During a baseball game, a batter hits a ball 1.4 meters above the ground with a velocity of 47 meters per second. This is kind of a weird scenario. I don't know baseball very well, but I would maybe call this a bunt, right, where they just kind of tap it. It's just the world's fastest bunt. Maybe it's Superman. Who knows? Either way, we are going to key you in. It's a horizontal projectile because we're telling you it's perfectly horizontal to the ground. You might also notice you have horizontal and vertical scaffolding. That's another way to know this is a horizontal projectile problem. We'll use our shortcut here, x equals negative 4.9 times t squared. And over here on the horizontal side, x equals vt. And we're just going to plug our numbers in. Negative 1.4 equals negative 4.9 t squared. Divide each side by negative 4.9. And we will get what t squared is. That tells us that t squared is equal to 0.286. And we'll find that our time is equal to 0.53 seconds. Bring that over here. We can plug it into x equals vt. We will find that that ball traveled a distance of 24.91 meters. There's a reason that you don't see batters hitting the ball perfectly horizontally intentionally. You would get a lot more distance otherwise, but that's a topic for another day. Let's take a look at number 9 through 11. These are conceptual questions. Here we have two identical objects, A and B. They're thrown from a cliff. Object B is fired from the cliff at 15 meters per second while object A is dropped. Which one will hit the ground first? Well, if we're looking through here, object B is fired from the cliff, object A is dropped. Their free body diagrams are both going to look like this because they are both only under the influence of the force of gravity. That means they're going to hit the ground at the same time. What page number did you find that information on? I'll be honest, I don't remember off the top of my head. It'll be there in the pictures of this review guide key. We now fire object A with twice the velocity of B, a velocity of 30 meters per second. Which hits the ground first now? They're going to hit the same time still, because again, that horizontal velocity only affects the side-to-side motion, not the time in the air. Now, this next one tends to trip people up. We are launching both objects with the same velocity, but we've now made object A have twice the mass of object B. Now, you might recall that mass is not one of the variables that we have really talked about in this unit or had an equation. That's in part because the mass has no influence on the amount of time an object spends in the air if you ignore air resistance. We can actually see this demonstrated if we either go to the moon and drop things like some of the Apollo astronauts did when they dropped a hammer and feather on video when they went to the moon and showed that without air resistance, the hammer and feather fell at the same rate. We also can see this in action down in Florida, where at NASA they will take a giant chamber and suck all the air out of it. We've actually seen them drop a large feather and a bowling ball at the same time, and both those objects hit the ground at the exact same time because they've sucked all the air out of the room, so there's nothing to resist its motion. As with all of these, check the review key pictures to find out which page numbers that information was on. Last page. We need to talk a little bit about symmetrical projectiles. So symmetrical projectiles are always our objects shot straight up into the air and then allowed to fall straight back down, landing at the same height they were launched from. This is going to give us a couple key pieces of useful information. One of those is that on the way up, this is always moving towards a top point where at the peak, A is negative 9.8 meters per second squared still, and velocity is 0 meters per second. That acceleration is what makes it start to speed up downwards after it reaches the peak. Problem number 1. An underground sprinkler system is shooting water straight up into the air. A little bit of an odd choice, but you do you. The stream of water rises to a height of 4.2 meters above the ground. Okay, so it's going to be going 4.2 meters up. We want to know, what is the speed the water is going as it hits the ground? Oh, well, so on the way down, right when it hits the ground, it's going to be moving. That's going to be the final velocity of the way down. So that's where I'm going to put my question mark. I know that it went to a height of 4.2 meters above the ground, but that also means that it's going to fall 4.2 meters from its maximum point. Now I know on the way up, whatever speed it left the ground with, at the very peak of its upward motion, it'll be moving at 0 meters per second. That same peak tells us that our acceleration is negative 9.8 meters per second squared, which is true for the way down as well. Now, one thing I do know is that on the way down, I'll be starting out from that peak point. So on the way down, my initial velocity is 0 meters per second. Now, if I'm looking at my problem here, right, I seek to know what V2 is. I know X, I know V1, and I know A. That means I can use the equation V2 squared equals V1 squared plus 2 times A times X. Now, I'll plug my numbers in here. V2 I still don't know. V1 I know is going to be 0. 2 we leave as is. A is negative 9.8. X was negative 4.2. So now we can run our numbers. 2 times negative 9.8 times negative 4.2. And we'll get V2 squared equals, since 0 squared is 0, it's just going to go away. We'll get the result of that multiplication tree, which is going to be 82.32, and then we'll leave our units off because they're kind of nonsensical when it's velocity squared. Now what we need to do is take our square root to get rid of that v2 squared, and we will find that v2 is going to be 9 meters per second. Now, conceptually, I understand that v2 in this case is going to be the speed at which that object strikes the ground. We lost the sign of our answer in here, so I can always say that v2 is negative 9 meters per second. Honestly, we will probably take either answer from you of positive or negative 9. I like that negative on any number that's pointing downwards. So for my students especially, I do want to see a negative on that v2. Right? That shows me that conceptually I understand that we are always calling down negative, which matches our acceleration. Now our next question is, how long is a drop of water from the sprinkler system mentioned above in the air? Now, we have a wealth of information now. We're going to carry all of our information down here. We know it went up 4.2 meters, it fell 4.2 meters. We know that it came to a stop at the top of its flight on the way up. We know it started from that stop on the way down. We know it struck the ground at negative 9 meters per second, and we know it left your hand at 9 meters per second. We know that it left your hand at 9 meters per second because your impact velocity is the opposite of the velocity that you threw it at, and vice versa. We know A is negative 9.8 meters per second squared because water and underground sprinkler systems are generally found here on the planet Earth. If you can think of somewhere else that you would find that underground sprinkler system, please let me know. I'm very curious. Now here my goal is to find time. I can find that on either side of my equation. I like working with upward motion sometimes, so what I'm going to say is v2 equals v1 plus at. It contains all the information I need. 0 is something I know. I know v1 is 9, a is negative 9.8 meters per second squared, and I don't know my time. I'm going to subtract my 9 over to the other side to get negative 9 is equal to negative 9.8 times t squared, and I'll undo that multiplication with a little division. And I'll find out that my time, that's not time squared. My brain ran away with itself. I'll discover when I run my calculations that my time is about 0.9 seconds. Now, keep in mind, I was asked how long is the drop of water from the sprinkler system in the air. I've calculated the amount of time it took to get to its peak. If I draw myself a little picture here of this motion, well, I know that it took 0.9 seconds to reach its peak, and I know that due to it being a symmetrical motion problem, the time is equal on the way up to the way down. What that tells me that I need to do is take my answer and double it to get the total time in air, because half my time was spent getting to the top and half of my time was spent falling. My time is 1.8 seconds. All right. Home stretch. Next up, a gun fires a bullet with a velocity of 320 meters per second straight up into the air. With what velocity does this bullet hit the ground? Well, it hits with negative 320 meters per second of velocity. I know this because symmetrical projectiles are built around symmetry. What that means is the time it takes an object to reach the peak of its flight is going to be equal to the time it takes that object to fall back down. The distance that an object travels upwards is going to be equal to the distance that the object falls. The distance an object is thrown with is going to be equal to the velocity it's thrown with is equal to the velocity it strikes the ground at. Now, the sign is going to be different because on the way up, you are pointing in the positive direction. On the way down, you're pointing in the negative direction. And so these values are going to be negative. We don't have to worry about the negative for time because time only travels in one direction. We can't travel back in time, as far as we are aware. If someone figures out a way to do that, please let me know. I have already made a couple mistakes in this video and would love to go back and correct my mistake. Again, page numbers for this information will be on the key when it's posted. Alright, we're referring to the bullet from question number 2, and we want to know how high up does this bullet travel. We're going to assume that somehow it was fired from ground level. Well, I want to know the height, and I could find that on either the way up or the way down. I do know it was fired upwards at 320 meters per second, and that at the peak of its flight, it would have stopped because it's projectile, and when you fire a projectile straight up at the peak, its vertical velocity is 0. Now on the way down, we'll start from 0 meters per second, and we'll strike the ground at negative 320 meters per second, which we know conceptually from above. Our acceleration is always going to be negative 9.8 meters per second squared here on Earth. And so we're actually left with a wealth of information in order to solve for how high does the bullet go. I could use the way up or the way down. Now, I like to work on the way up, and so I'm going to work on the way up, where I know V2, I know V1, I know A, and I'm looking for X. I'm going to write out my equation with no numbers plugged in, and this is just a reminder, everyone. You do this because we notice students make fewer steps when they do this, and we award you a point for doing this on your test, so make sure you do it so you're not losing those points. I'll plug my numbers in. And I'm just going to work through and simplify my equation a bit. 320 squared is going to be 102,400. 2 times negative 9.8 is going to be negative 19.6. I'm going to subtract that 102,000 number over to the other side. Leaving me in this situation. And now I'll be able to divide each side by negative 19.6 to solve for X. And we'll discover that our distance traveled is about 5,224 meters, 0.5. Well, I hope this video was helpful to you if you are working on your review. If you still have any questions, please be sure to let us know. We're here to access us via email, ASR, or whenever you can find us. Your test is coming up, so make sure you use your time well. Thanks for watching.